basithathela abazali.
Hello guys, how are you doing? Okay, good. Okay, so now we're going to start with work energy. So it's work energy, and power. So already energy we have done from the previous grades, from grade 10, but we'll also revise it later on. Okay, so now we're going to discuss work. So work, I get, in everyday life, when people babolela, yo, hey, go school for too much work. Hey, the school is too much work. Yo, I have too much work to live. And I'm not going to work if you are, But actually in physics, it means like something which is very, very different. So we can say work. So we're going to start with work. Okay. So we're going to start with work. So basically work, when we are dealing with work, we are talking about the transfer. Work is basically the transfer of energy. Transfer of energy. When there's a transfer of energy, that's work. Is the transfer of energy. Basically, when you are transferring energy, you are doing work. Okay. That's why when how about bereka or something, you need to work first. You need to have energy. You can't work if you don't have energy. That's why go school tonsule ka breaki let's amailo ja. Then cause little get otherwise you cannot concentrate because you cannot do any work. But once you have energy, once you transfer that energy, that's work. Okay, but physics, the most important thing about work is that work, when you talk about work in physics, basically we say the work done. The work done on we basically say the work done on an object by a force. There's something that you discuss here, which is very important. The work done by a force is a what? The work done by the force is the product of the displacement, and the component of the force. Component of the force parallel to the displacement. Okay, so basically we talk about what when you apply a force on an object and then the object accelerate in the direction of the displacement, then we say somebody is doing work. Let's say, for example, we have the following block. Okay, let me just write in another sheet of paper. Okay, so let's say we have a block, the block with the mass of m, then apply a block and apply a force. So this force, provided this force is a constant force, then this block is going to move. So basically when we talk about the displacement, delta x is basically our displacement. So when I apply a force on an object, so this object is going to accelerate in this direction, it's going to move in this direction again. So the direction it's among kayon, if the block is going to the left, I'm pulling the block and the block is going to the left, it means the displacement is created in the left, to the left. So if I'm pushing this to the right, it means the displacement is created to the right. Okay, so now this is my block. I have applied the force, then yazama with the flowing displacement. Then this is my displacement. Okay, so we applied a force of x, we apply a force on the block, then it accelerated. Okay, then we're going to say work is basically, so now we say work W is equals to the force multiplied by the displacement. Then we talk about cos of theta. So we'll discuss this cos of theta. Okay, so now what we have, W is what we call, this one is our work. W is my work, and then this one, it is measured in joules, because we said work is transfer of energy, so it means it's in joules. J, it's energy, it's also form part of energy, joules. Then we have F, which is called our force. F, which is our force applied. You can say force applied or anything. So this one is measured in newtons, and you know the force measured in newtons. Then we also have delta x, which is our displacement. Which our displacement it is measured in meters. This is what we have. Okay, our displacement. So basically work is a scalar quantity. Work is a scalar quantity. So but we just have positive work, and then we also have the negative work. Okay, so now this cos theta is the one that will help us to know whether are we doing work or we are not doing any work. To determine whether are we doing work or we are not doing any work done. Okay, so this is how we get it. And then so now what do we have? Let's have an example. So let's have an example. Then I will discuss this thing with an example. Okay, so now let me just take this. We have an object, okay, 2 kg, and then it's pulled by a force which is 50 newtons. Then we also have friction, which is 10 newtons. We also have friction, which is 10 newtons. Okay, so for you to understand these questions, the first thing that you need to understand bargain Newton's second laws. You remember the questions are Newton's second law. So from here I can draw my free body diagram. I know I have Fg going down, then I also have what? I also have the normal force. So this thing is being, let's say, is being pushed 5 meters. Never. So we want to calculate the work done. So let's say this one is the force applied, and then always when you use the forces, they must be in parallel. They must be parallel to the displacement. That's what I must know. They must be parallel to the what? To the displacement. Okay, so now let's say we have this. Then what are we going to do? We want to calculate the work done. So you want to calculate the work done by the force applied. So if I say work done by the force applied, it's going to be work done by the force applied force is going to be F multiplied by delta X, then cos of theta. Then how are we going to know whether, so more theta can be, so theta can be 0 degrees, can be 180, can be 90 degrees. We use this. So if the displacement is in this direction, displacement is in this direction, and then also the force that is applied is also in the same direction with the displacement, there's a 0. You put 0 between them because they are in the same direction. The force applied is going this way, and then the displacement is going this way. Between them we're going to have 0 degrees. And then when it's 180 degrees, it's when, if the block is going this way, the block is going this way, and then the force is going this way. We have a force that is going in an opposite direction. They form 180 degrees. Because how can check this block? If the block is going to the right, the displacement is created to the right. Displacement then let's say the force acts in the opposite direction, usually friction. You are 180. Sorry guys for the network. It's not favoring us. So when we have this one, it's 0 degrees. And then also another thing, if the displacement is also going this way and then the force is going up, they form 90 degrees. So basically when they say, so again we have theta here. When theta is equals to 0 degrees, they are in the same direction. Again, they are in the same direction. We are doing a positive work. We say here we are doing a positive. And we are doing a positive work. Okay, and we are doing a positive work. Okay. Okay, so now then if our theta is 180 degrees, the inner opposite is negative work. It's negative work. This one it shows us where we are taking into the system. This one we are putting into the system. Then a 0, there's no work. And then a normal 90 degrees. When theta is equals to 90 degrees, no work done. No work done. There's no work done. Okay, so now I want us to calculate the work done by the applied force. So we said the work done by the applied force is equals to, we're going to say the applied force multiplied by the displacement and then cos of theta. So what is the applied force? It's 50 newtons. Then what is my displacement? It's a mailing. It's 5 newtons. Cos of, then the theta how? Since now the applied force and the displacement, they're in the same direction, you're going to put 0. Okay? Then how we have 0 molar, you're going to say 50 multiplied by 5. Then you get 250. You get 250 joules. So basically 250 joules is your work done by the what? It's your work done by the applied force. Okay. Then now we can get, let's get the work done by the frictional force. Work done by the frictional force. F frictional multiplied by delta x, then the cos of theta. Okay. Then a frictional force. What is my frictional force? Is 10 newtons. What is my displacement? Displacement is going to be 5, still 5. Then cos of, then theta arena. How can check? Your frictional force is going to the left, and then but your block is going to the right. Whatever. So they are in opposite direction. So it means they're going to form 180. So it's going to be what? 10 multiplied by 5, which is minus 50 joules. Whatever. Which is minus 50 joules. Okay, then now I want us to calculate the net work done. I want us to calculate the work done by the of the very same situation. Just want us to calculate now the work done by the normal force. I want us to calculate the work done by the Fg. Fg is a gravitational force. Let's check. Equally Fg multiplied by x, then cos of theta. So we check Fg, right? So Fg is equals to mg delta x, then cos of theta. What is this? This thing gives us 2 multiplied by 9,8. Then this one is going to be 5. Then cos. Fg is going down, mg is going up. Whatever. Fg is going down, and then this thing is going to the right. So they form 90 degrees. How we substitute the for a work done here is equals to 0. There's no work done. Similarly, the work done by the normal force will also be equals to 0. They were doing no work. Yeah? Then we can calculate the net work done. Again, net force, also the net work done. The net work done, it means you are calculating the sum of all the work that we have. So we have work done by the applied force plus the work done by the frictional force plus the work done by the what? Plus the work done by the normal force plus the work done by Fg. So you realize for this one we got how much? For the first one, by the applied force we got 250 plus this one we got minus 50 plus 0 plus 0. It means now that our net work is going to be 200 joules. It's positive work. So the sum of all the net work done on an object, it gives us how much? It gives us 200 joules. Okay. So this is how we can get the net work done. Okay. So now another thing. So this is how we can get the net work done on an object. We can also use another formula. We can also get another formula. So we got 200 joules. So keep this formula in mind. Then I want us to do it another way. Are we also going to get the same answer now? So let us go back to the same problem that we have. Yeah? So now we have the problem. It's the problem. So basically, right, they are perpendicular to the motion. Basically, they refer the work that is 0. So we don't have to include them. So okay, check out from this graph, from this what we have. If I say net work, I'm looking for what? F net multiplied by delta x is equals to cos theta. Then I need to find my F net. And what will be my F net? My F net is going to be sum of the forces. So since I chose to the right, this block is going to the right. Usually we take the direction of the motion as positive. It's going to have F applied plus minus frictional force. So we have 50 plus minus 10. We have how much? 40 newtons. Yeah, we have 40 newtons. Then when we calculate the net work done, so kacheka it's 40 newtons. The resultant is also going to the right. Level is also going to the right. It means the displacement and the then F net, they're going to the same direction. It means our theta is equals to 0. Then our net work done is going to be equals to F net delta x then cos of theta. Then now we can substitute. What is our F net? Our F net is equals to 40. What is our displacement? Our displacement is equals to 5. Cos is going to be cos of 0 degrees. Then what do we have? We're going to have 40 multiplied by 5. We get 200 joules. This is the very same answer that we got. It's the very same answer that we got here. You remember, man? So now, so far, so this is what we have for this solution, for this problem. That's nice. Okay, so now we need to know how to use this formula very, very well. Okay, so what we have learned so far. Is that work net is equals to F net multiplied by x multiplied by cos theta. This is the formula that we have learned so far. Okay, so let me take another example. Let's say we have a block also put like this, and the force is 50 newtons. The angle between them is 30 degrees. We have the angle between them is 30 degrees. Then it's also 2 kg. Then the displacement is also 5 meters. Then we have the frictional force as 10 newtons. It's a very same problem, but now it is pulled at an angle. So when it's pulled at an angle, the force that we're looking for is basically the Fx, guys. We are using the horizontal force, not this one. So we know that our Fx is basically F then the cos of theta. You remember this, Mosagir? It's going to be F the cos of theta. So now, when you are looking for the work done, displacement must be parallel. This thing, they must be parallel to the motion. So this one is not parallel to the motion. We're going to use its Fx. So now we have to, if we can draw, it's very important to know how to draw a free body diagram. A free body diagram is also important, guys. Free body. Right, okay, we have this, Fx, Ff, Fy, normal force, Fg. Yeah, this is what we have. Okay, so now we can calculate the F net. Yeah, so what will be my F net? My F net will be Fx plus minus frictional force. Yeah? Horizontal. This thing is only moving horizontal. It's moving horizontal. So we cannot include these ones. So this is what we have. So what is my Fx? My Fx is going to be F cos of theta plus minus Ff. So we have basically 50 cos of 30 minus what? Minus 10. Then it's going to give me how much? So we have 50. So we have 50 cos of 30 minus 10. 50 cos of 30 minus 10. Then if you punch it on your calculator, you get 33,301 newtons. This is our F net. You know why? It's very important, guys. That's why high. When you pull things straight, so low pull an angle, basically we are not applying the same force because of how pull angle now. It's like you are lifting it so that you reduce the friction. That's why pula an angle. That's why the F net here is much smaller than the one that we got from the previous question. So we have the F net now. So now we can calculate the work done by the F net. So we can calculate the work done, the net work done. So F net, work net is equals to F net multiplied by X, then cos of theta. Then what do we have? Then we have F net, which is 33,301 multiplied by 5, then cos over cos of 0, because they're in the same direction. Then you punch your calculator. We have multiplied by 5, then we get our answer to be 166,51 joules. This is our net. So they can ask you many questions. Determine the work done by the applied force. Determine the work done by the frictional force. Right? So now, as long as you know how to use this formula, then we know what then we are good to go. Right? Then we are good to go. Okay. So now I just want us to do another example using an inclined plane. I want us to do another example using the inclined plane. So let's say we have an inclined plane. 30 degrees. We have the inclined plane, which is 30 degrees, and then let's say this object is just going down. Let's say this object is just sliding down. Okay? Then they say calculate, then it's sliding down with the displacement of 5 meters. Sliding down, and then it's a 2 kg block. It's sliding down. It's just sliding down. Look at this thing. So for this one, what you need to be careful of, we know how we have FG. FG is always perpendicular to the motion. This is FG. And then we also have normal force is also perpendicular to the surface. This is what we have. These are the forces let's say we also have friction. We have the frictional force. If it's going down, it means the frictional force will be up. Then we have two components. The components, we have the FG perpendicular, then the FG parallel. So we know this thing from grade 9. No, from grade 11, man. Okay. So let's say they want us to calculate the work done. Calculate work done by gravitational force. Okay, I must specify. I want a gravitational force. So for example, we have many components like one, FG parallel, FG going down. So I must specify FG bara FM. So how say it, guys? You have to know these things, right? So you got so fit challenge. So you can use either. So if I calculate the work done by the gravitational force, if you use this one or this one, you're going to get the same answer. Let us use the one here, FG parallel. So if I calculate the work done, so you can just use the one here. Yep, yeah, this thing in a parallel motion. You can use this one in the parallel motion. Where are those things? Where are my markers? So we can use this one in a parallel motion. We're very excited. So rotobale work done by FG parallel. So you have right mg sin theta delta x cos of theta ne la bona mosagere. So it baleng mg ya rena m ya rena ke 2 9,8 sin of 30 delta x ya rena ke 5, then cos of it's going down cos over 0 degrees. There we go. Then let us calculate using our calculator. You can see we have using our calculator. So you can see what are we going to have. we're going to have where are my markers? So here we calculate the 2 multiplied by 9,8 sine 30, then cos of 0, because they're going in the same direction, it's going down. So what do we get? We get 9,8 joules. Okay. Then R1 here, so work done by FG, just FG. Scoba FG delta X, then cos of theta. This one it will require you to do some work, because we have a incline like this, okay? Theta 30 degrees more. So it's a delta X. So it's a delta X more. Because FG is going down. Level. Refine this one. Distance. Class. So refine distance here. Basically we can use sine. Well, so basically sine of 30 degrees. Sine of 30 degrees is equals to how much? Is equals to d over delta x. Well, so basically composite delta x is equals to d is equals to delta x sine of theta. Delta x sine of theta. Right? Is equals to delta x sine of theta. So ngana is equals to mg delta x here again. I'm looking for d modes, ne? D over delta x. So d is going to be going down. Is going to be delta x sine of theta cos of theta. But theta is direction. So kura robali 2 multiplied by 9,8 delta x like 5, then sine of what? Sine of 30 cos they are going in there. FG is going down, D on is going down. So kura robali 0 degrees. So go 9,8 joules. So whether you use this formula or use this formula, you're going to get the same answer. But my advice to you is that every time you calculate the work done by the gravitational force, use the FG parallel, because it's just easy. You just substitute over, just easy. I'll talk you we read these things with the copy set for, because whether you use this one or use this one, we get the same answers. Okay. So yeah. Okay. That's good. That's good, guys. Okay. So now then now you can use that formula to get the work net and everything. So far we have explored this formula. So far we know that work net is equals to F net multiplied by delta x, then cos of theta. This is what you need to know so far. This is what we have so far. Okay. Then we'll explore other things. We'll explore other things later. Maybe tomorrow. Okay. So thank you guys for watching.
She was a